Thank you. I'm glad to present today on behalf of the Ginan team an overview of Geoscience Australia's most recently developed open source GNSS analysis center software called Ginan. And I'd like to just highlight that all the work has been done by the Ginan development and operations team in Geoscience Australia with academy and industry partners, and today I'm only presenting on their behalf. So, to start with, the Ginan name comes from the Australian First Nations Wardaman people of the Northern Territory in Australia. It is a Wardaman word for a red lily bag filled with songs of knowledge, and it is also the fifth brightest star in the Southern Cross, which helps the First Australians to navigate. Ginan, in terms of how it fits into our national positioning infrastructure capability, NPIC is used to validate and verify the data coming from the NPIC network to make sure that the users are accessing data, only data that is verified and qualified, to give them access to the 3 to 5 to the centimeter accuracy levels. So Ginan is a comprehensive open source suite of software for precise positioning. This slide highlights some of the high-level features of Ginan. The figure shows the special advantage that Australia has in terms of its visibility, which allows us to track multiple GNSS positioning signals, and Ginan is designed and built to exploit this advantage that we have in Australia. The philosophy is generally on different observation processing strategies. It can do both network mode and user mode, single state space representation, point positioning, precise point positioning methodology, uses a dynamic, robust, extended Kalman filter estimator, including smoothing, both fixed lag and backward full RTS smoothing. Supports both real-time and post-process analysis, both static and kinematic at the same time. The same software can do both real-time and post-process and static and kinematic. It outputs industry standard IGS type products as well as the stream-based positioning products. Other capabilities are precise orbit determination, low Earth orbit estimation, and SLR processing, and it is open source. In terms of the architecture and components of the software, configuration is done by a standard YAML file. Input files are both post-process Linux type of file, for example, or streams for real-time processing. Multi-GNSS observations, always on difference, multi-frequency on combined, or dual-frequency on dispute-free observations are processed. For the modeling, usually all the IGS repository standard models are implemented for most of the components, and IGS 2010 compliant models. In terms of the estimation, as I said, a Kalman filter, which is tightly coupled with an orbit propagator, and a backward smoothing is implemented. Data pre-processing is implemented, as well as in-filter error detection on both measurements and states. There's an augmentation component as well, which does minimum constraints, ambiguity resolution, and NoSQL modeling. And the outputs are IGS type products, as well as RTCM3 and Compact SSR stream-based products. There's also a Mongo database integration and a web-based exploratory data analysis visualization, which is linked to the database for visualization purposes. Now, give an overview of some of the use cases and comparisons against the IGS type benchmark products, and also other benchmark data. So this is an example of a kinematic PPP solution from Ginan. This is using 30 days of data, 30-second Linux data over 30 stations, using 5-minute and 30-minute IGS clocks. So as you can see, this one, yeah. So in terms of, so these are the horizontal component differences compared to the IGS final sonic solution. So the mean differences are, as you can see, at the millimeter, 1 and 3 millimeter for horizontal and 1 centimeter for the vertical component using the 5-minute clocks. However, 5-minute clocks lead to standard deviations of 7 and 5 centimeter horizontal and 13 millimeter vertical. However, once we move to the using the 30-second clocks, the standard deviations are vastly improved to 1 centimeter level horizontal and 3 centimeter level vertical. The next example is from the static PPP results. So the difference here is that we don't introduce any process noise level, so we estimate an aggregated position over the 24-hour period. So this example is over 7 days of data on the same 30 stations using IGS final 30-second clock estimation, and again comparing to the IGS final solutions. The mean differences are at the level of 0 to 1 millimeter horizontal and 3 millimeter vertical, and standard deviation at the few millimeter level horizontal and centimeter level vertical. The figure on the right-hand side is shows how inclusion of additional data improves the consistency of the estimates compared to the IGS solution. So essentially, after about inclusion of 1 hour of data, we reach 5 to 10 centimeter accuracy levels, and after about 6 hours, we reach millimeter to centimeter level accuracy levels. The next example is the network processing and orbit estimation. Just before that, an important aspect of Ginan is that the Kalman filter, or the parameter estimation algorithm P, is tightly coupled with the orbit propagator and estimator. So essentially, the orbit estimator propagates the orbits epoch by epoch, and variational equations are computed epoch by epoch based on the previous Kalman filter orbital status update. So essentially, the P feeds the updated states into the pod, which is the orbit propagator, and at each epoch, the predicted states from pod also feed into the estimation algorithm. And this works for both post-process and real-time applications. The epoch by epoch propagation of the orbits allows for automatic detection and estimation of non-dynamic orbital accelerations like satellite maneuvers, and usually when it happens, a huge process noise is implemented so the satellite can reconverge to the new position and velocity estimates. So in 2020, Lasser et al. Provided benchmark data for verifying background model implementation in orbit and gravity fields. So they used group software to model one-day arc of the grace to provide some benchmark data for validation and comparison of the different software. So the figure on the top is so what was done was Ginan was used to reproduce the results and compare the Ginan results to the benchmark data. The figure on the top is the different background model, the differences between the Ginan estimates to the compared to the benchmark data for the different background model, and essentially anything below that dashed line is considered acceptable. And the figure on the bottom is how Ginan compares to the different software in the benchmark data comparison in terms of each of the background models. And as you see, usually most of the background models, Ginan sits somewhere in the middle. So an example of the network processing for 2 days of data over 96 global tracking stations, where the Ginan was used to estimate station positions and other parameters, as well as the orbits and clocks. So the histograms here show the difference in the position differences with the IGS weekly combined solution, and the differences are at 2, 4, and 8 millimeters for the northeast and up components. This slide shows the comparison against the IGS comparison of the orbit estimated by Ginan with respect to the IGS rapid for the set of GPS satellites. So you see the differences are 1.5 centimeter, 2.5 centimeter, 1.7 centimeter in the radial long track and cross track components. The next slide shows the comparison with the IGS rapid clocks, and the differences are at the level of 63 picoseconds, equivalent to about 2 centimeter range error. And the last slide shows the Ginan LEO orbit estimation capability. This is a result of comparing Ginan with the level 1B Grace follow-on satellites provided by the JPL. So the differences are, when using the kinematic orbit estimation, the differences are at the level of 5 to 7, approximately 3D centimeter 3D RMS error, but when using the reduced dynamic approach, the differences are at the levels of 1 to 2 centimeters in the 3D RMS error. And the figure below is the epoch by epoch differences, where you can see residuals 1 per rev for the different comparisons. With that, thank you, and I guess we feel free to ask questions. I'll try to answer as much as I can, but otherwise feel free to contact directly to the Ginan team, as well as the software and documentation on the GitHub page. Thank you.